Alright, today I would like to talk to you about levers, one of our types of simple machine. So, some things to know about levers. They are a type of simple machine. Let's move this up here. They have three parts. There's an input part where you put your effort, your force into the machine. There's an output, also called the load. That is what you're moving with a lever. And the fulcrum. That's your pivot point, the spot where the fulcrum or the lever turns. And there are also three types of lever: first class, second class, and third class. So first, we're going to talk about the first class lever. So there are three parts. First class lever always has the fulcrum between your input and your output. Okay, now that doesn't necessarily mean it has to be in the middle. You can have the fulcrum to one side and still have your input and your output. These arrows represent the direction things are moving. You could also have the fulcrum and your input could be lifting while your load moves in the other direction. So I'm going to erase these here, and we'll draw another lever. Alright, so I have my lever here, and I'll put my fulcrum right there. Now we have this large box that we want to lift. Now in order to get the box to move up, I'm going to have to apply a force in that direction. That's my force in. Now the force on this box is going to be force of gravity trying to pull that box down. So I have some forces, and this is going to equal the force out. So this is the force I need to apply to get this to move. The other factor we have is our distance. So our distance our input distance is the distance from the fulcrum to the point where we are applying the force. And our output distance is the distance from the fulcrum to the point where our load is located on our lever. So if I look at another example, if I have a lever here, and a long arm this way, and my load is still on the box, my distances do not have to be equal. Okay, and that'll be very important because the length of this lever arm plays a big part into how much force you actually have to put into the machine to get your load to move. Alright, so what I want to look at is homework question number 3. So I have a screwdriver that I'm using as my lever, and I'm trying to pry the lid off a can of paint. Alright, so the question tells me the screwdriver used to pry open the can of paint is 23 centimeters. The entire screwdriver is 23 centimeters. A force of 84.3 newtons. So I'm pushing down on my screwdriver with 84.3 newtons of force. That would be my input force. This would be, this is the total distance of the screwdriver. What force is on the lid, which is 2 centimeters from the other end? Okay, so I want to know what force am I getting out of my lever? All right, so if I simplify it here, here's my lever. There's my fulcrum. This distance here is 2 centimeters. And I'm getting some force out of it. That means this distance here is going to be 21 centimeters. My whole screwdriver is 23 centimeters. My fulcrum is located 2 centimeters from the end of the screwdriver. That means this section here is 21 centimeters. And I'm putting a force in on that end of 84.3 newtons. Switch to yellow for the calculations here. So my force in times my distance in is going to equal my force out times my distance out. And there's lots of ways you can come up with this. One of the bigger ones, mechanical advantage. F out divided by F in equals D in divided by D out. If you manipulate that around, do cross multiplication, you end up with this here. Okay, so my force in is 84.3 newtons. My distance is 21 centimeters, but remember we always want to use meters. So I'm going to go with 0.21 meters. That's going to be my mystery force out times 0.02 meters. So if I divide both sides by 0.02, this goes away, and I end up with F out equaling 84.3 times 0.21 divided by 0.02. I'm getting an answer of 885.15 newtons. We use 3 sig figs. That's what I'm getting for an answer. And if we check our answer key in our packet, homework question number 3, 885.2 newtons. They went out to 4 sig figs. Same answer we got. We got the right idea. We know what we're doing. Wonderful. And so that is a first-class lever with the fulcrum located in between your output and your input. Next, let's take a look at a second-class lever. So for a second-class lever, that's something like a wheelbarrow. With a wheelbarrow, our pivot point, our fulcrum is located right there. So this would be our fulcrum. Our load is right here in the middle. This is our load. This is what we're trying to move. And then our effort, our force, comes here by lifting the wheelbarrow. So there's our force in, and our force out. Gravity is pulling our load down. We want it to move upwards. Now, if you'll notice one little difference here between the first class and the second class, I'm going to draw my fulcrum way out on this end. Our load has some distance, D out. That's for our force. And our input overlaps our output distance. Because remember, the distance is measured from the fulcrum. In terms of solving a problem like this, the setup is the same. Force in times the distance in is going to equal the force out times the distance out. Just make sure you're measuring the right amount of distance and you're properly identifying your forces. Okay, last we'll go over a third class lever. Okay, so a third class lever, third and final lever. Again, this one has the fulcrum at one end. And we're just switching our input and our output. Examples of this one are a broom, okay, so with a broom, your upper hand, that acts as your fulcrum. Your middle hand is going to push on the broom this way. This is going to be your input force. This would be your input distance. And lastly, your output force is the broom actually pushing all the detritus. And that distance will be measured again from the fulcrum down to your force. And then solving this just like the other ones. Force in times your distance in is going to equal your force out times your distance out. So those are your three types of levers. One of the biggest things will be identifying the type of lever you have and then being able to solve for forces and distances based on the type of lever. The last thing I have for you on Schoology, I'm going to add a challenge question. I want you to tell me how long of a lever would you need to lift the earth. So we're going to use this same idea, force in times the distance in is equal to force out times the distance out. You get to create your distances. The force in will be you standing on one end of your lever, and the force out would be the earth. So here's a quick view of what that would look like if you chose to use a first class lever. You have your lever, your fulcrum, the earth is here, and we're going to just, for fun, we're going to call this force Fg. So find the mass of the earth, multiply that by the 9.81 meters per second squared. I know the force of gravity on the earth wouldn't be the same thing, but it's just for fun. And then you'll have you standing on the other end of the fulcrum. There we go, the person has a neck. And again, you're going to consider yours also Fg, your mass times acceleration due to gravity. You get to choose the length of your lever arms. And I basically want you to tell me, based on whatever this distance is, what does your input distance need to be to lift the earth? Good luck, and I'll talk to you again tomorrow.